All right, let's run through these questions, okay? A die is rolled many times in a board game. The player is considering whether the die shows more sixes than it should. That is, she feels the number 6 came up too many times and now is questioning whether this die is fair. Is this one or two-tailed? I think this is one-tailed. And the reason is, let's see, yeah, the null hypothesis is that the probability of getting a 6, I'll write P6 like this, that is 1 over 6. And then for part C, oh, thanks Angela, I didn't even bother to look up. The alternative would be the probability of getting a 6 is more than 1 over 6. Are we happy with that? Yeah, and you understand why it's like this? Because she wants to know if you're getting more 6s than you should. Okay. 2. A boy tosses a coin 100 times and would like to know if the coin is fair or biased. Is this one or two-tailed? So this is two-tailed. And the null hypothesis is that the probability is a half. And then the alternative hypothesis is that the probability is not a half. Okay. Is that okay so far? Yeah. 3 students are playing a game with a die in a casino, and they each suspect that a 1 shows up more than it should. What are the hypotheses for this claim? Okay, so for the first one, the null hypothesis is that the probability of getting a 1 is it's a die, is it? Yeah, 1 over 6. And probability, the alternative hypothesis is that the probability of getting a 1 is more than, or, well, actually, hang on, let's see. Not equal to 6. Oh, sorry, a 1 shows up more than it should, sorry. So that's more than 1 over 6. And then the, that's A. B, a 1 does not show up as often as it should. So a 1 not showing up as often as it should. So the hypothesis is that the probability of a 1 is a 6, and the alternative is that it's not a 6. C, a 1 shows up less than it should. Okay, so I see what I did here. The hypothesis is that the probability of a 1 is 1 over 6, and the alternative is the probability of a 1 is less than 1 over 6. Okay. 4 now. James Bond is given a sample of drinks which have either been shaken or stirred. We would like to know if Mr. Bond can tell the difference between shaken or stirred. Is this a 1 or 2-tailed test? So, if we think about, I'm asking whether he can tell the difference between if they're shaken or stirred. So, the null hypothesis and the alternative hypothesis. So, the null would be he can't tell the difference. So that means the probability that he guesses right is 0.5. So if he can't really tell a difference, and half the drinks are shaken and half are stirred, then if he can't tell a difference, you would expect him to get half of them right anyways. Hey Sylvia, are you talking to a student? Okay, great. And what would be the alternative here? What would be the alternative here? Yeah, not equal to a half. So, 1 or 2 tails? 2. Okay. B now. If instead we as the researcher would like to know if Mr. Bond can predict if a drink was either shaken or stirred, then is this a one or two tile test? So this one is a little bit different. The null hypothesis is still the same. Whoa. The null hypothesis is... Sorry, my laptop is acting up a little bit. It's going to take a second to catch up. Anyways, I'll just say it. The null hypothesis is still that the probability he's right. Hello? Come on. I don't know what's going on here. It's 0.5. It's catching up. And the alternative hypothesis is that it's more than 0.5. So, the tiny difference between the two is in part B, I use the word predict. So, if you want to know somebody's good at predicting something, that means they should be right more than just guessing. So, for example, if I flip a coin and I claim I can predict what is going to come up next, if I was right half the time, then I'm not really predicting anything because, I'm bound to be right half the time. You understand? So if the claim is I can predict what the next result will be, I need to be right more than half the time. That's what I mean. That's what we mean when we say to predict something, that you're more right than just guessing. Yeah. So it's only really because of that word predict. If you compare that with the last question, the word was difference. See, it's really, really a small distinction. Okay. Can I scroll down? Yeah. So we're now on to our first actual calculation, I think, are we? Yeah. 5. A coin is tossed 10 times and we get a head 3 times. We want to test if the coin is fair. So the null hypothesis is that the probability of getting a heads is half, and the alternative is the probability is not a half. That's fine. Calculate the p-value. Okay, so picture it like this. We got heads, what did we get? 3 times, wasn't it? Okay. And if this was true, how many heads would we expect to get? 5. Okay. So just before we do any calculation, we're already a little bit away from what we think we should get. Okay. So what would be more extreme? In other words, what would give me more evidence in favor of the alternative? Well, that's if I got 2 heads, right? That would be more evidence for the alternative. And if I got 1 head, and if I got 0, so 0, 1, 2, 3. But another possibility is that you could have been, rather than being too few, you could have been too many. So you could also look at 7, 8, 9 and 10 heads. In other words, if you want to try and visualize it, if you're here versus if you're here, in the red box we call these outcomes extreme outcomes, and if we calculate their value, that's called the p-value, and it's this that helps us decide which is more likely, the green situation or the red situation. The null or the alternative. Okay, so the p-value here is not too difficult to get because this guy here, we can get it from the tables, can't we? So what would I have to look up in the table book? I'd have to go to n is 10, isn't it? P is 0.5 and X is 3. Yeah. Also, I have to look at this. Now, I kind of think for this question, that calculation on the right, if you work it out, you'll get the exact same answer as on the left. But we can check it. So I need to plus. Now, the problem here is I can't look up 7, 8, 9, or 10, can I? So what I have to do is my trick of 1 minus, and then, yeah, I look up the table book at 6 with the 0.5. Oh, sorry. The n is still 10, the p is still 0.5, and the x this time is 6. Okay, so let's see. What page is that on now? 11, eh? Oh, here it is. You have it? It's not symmetric? You sure?
It is.
Yeah?
It's less than 3.
Hang on, let me see. What's the first one? 0. 0.1719.
The other is 0.8281.
But then 1 minus.
1 minus 1.
How is it 7 or more? It's not.
7 or more means 1 minus
Yeah,
6 or less. Doesn't it? If I said 7 or more heads, the opposite of getting 7 or more heads is getting 6 or fewer heads. Yeah. Is it the same? I think it's the same. I thought it would be. Anyways, no big deal. It's quite clear that this number here is more than 5%, isn't it? So, should we reject the null? Do not reject. Okay. Can I scroll down? Not yet? Okay. Okay. Scroll down. Yes? Yeah? Okay. The next one. What number am I on now? 6? A die is rolled 20 times and you get 10 sixes. Test the claim that it's biased in favor of given more 6s. So, I forgot to check if my answer's been right so far. Yeah, it has been. Okay. Right. So, what's the null hypothesis here? That the probability of getting a 6 is 1 over 6. And the alternative? Probability of getting a 6 is more than 1 over 6. Okay? How many 6s did we get in our 20? How many 6s did we get? What does it say? We got 10. Yeah? We got 10. So the p-value here, that's the probability of getting the 10 that you got. And what would be more extreme? What would be more support for the alternative? Getting more 6s or less 6s? If I want, yeah, more 6s. So it's 10 or more. Now, why don't I need to look at any mirror image? Because it's one tail. It's just one half. Okay. Unfortunately, we can't look up or more in the table book. So that is 1 minus the probability of 9 or less. So that's 1 minus table book. You go to the table that has 20 in it. Probability of 0.15 is the closest, and go down to 9. So 0. Are we confused here? 20, yeah. 0.999. 3 nines. Alright. 0.0002. This is certainly less than 5%. So, what is our conclusion? We reject unsurprisingly, we reject no. Are we getting into the swing of these? I know they can be a bit tricky. Let's look at 7 now. 7. A drug company, Pertec Drug Co., tests a new drug on 15 patients with the flu. It is known that 20% of patients get better after a week anyways. The drug company is claiming that her new drug improves the recovery rate since it's cured 5 patients. Test this claim. Now guys, medicine guys, well, even if you're not medicine, you're going to be doing something science, right? This is literally the exact thing you will be doing, or at least reading papers about. It's literally this, you know. Usually they get 15 students, or whoever's willing to volunteer, and then they test the drug on them and see what happens. So here, what is the null hypothesis? The null hypothesis is that the probability you'll get better in a week is 0.2. Now the alternative is that the drug helps you recover faster, so the probability is actually greater than that. Okay? So let's calculate the p-value. In our group of 15, how many people got better after a week? What did it say? What did it say? 5. 5. So the extremes will be 5 or more, which is 1 minus probability of 4 or less, which is 1 minus the table book. We need to go to 15, we need to go to 0.2, and we need to go to 4. So that's 1 minus 0.8358. So that's going to be roughly like 15% or whatever it is. It's definitely more than 5%. So what does that mean? Do not reject. So I ask you to comment. So what is the comment you would make here? Yeah, there is no evidence. Yeah, we'll just say evidence. Evidence to support the claim of improved recovery rates at the 5% level. Okay. Okay. Next one now. It's almost the same, except you've got a better, drug company. What's the only difference in Part B? Oh, well, there's two differences. You have 20 patients, and 8 of them were cured. Okay? So it's the same hypothesis. It's just a different result. So the p-value is going to be the probability. How many did I say? 8? 8 or more. Which is 1 minus 7 or less. Is it 7 or less or 7 or fewer, actually? 7 or fewer, isn't it? I know, it's true, but you know, I don't want to make your EAP teacher mad. So that's 1 minus, who is your EAP teacher? Oh no, screw him. Right, 1 minus the table, 20, 0.2 and 7. So what do we get here?
1 minus 1 minus 8, 7.
So it's slightly under now, is it? It's 0.04? 321. That's definitely less than 5%. So this is better. We reject the null. Okay. So what's our comment here? So would we say our comment is we have found a new drug that makes people better? No. No, because it's possible that, you know, just by chance these 8 people got better quicker. What we could say is, you know, we have some evidence in support of the claim of improved recovery rates. At the 5% level. And again, I just want to stress, this doesn't mean that the drug definitely makes people better quicker. Because like I said, out of dumb luck, you might have just gotten 8 patients who got better quicker naturally. So we do have evidence that the drug works, but this 5% here means that there's a 5% chance we're wrong. There's a 5% chance that we are wrongly thinking this. So all we've done is provided enough evidence to do another trial of the drug on a larger group of people, perhaps. You understand? Yeah. I should tell you why this statistic stuff came about. It came about must be about 100 years ago. A biologist and statistician called Fisher. I don't know if you do him in biology. Do you know if you Colin ever mentioned this guy, Fisher? No. Basically, Fisher is the guy who came up with all these tests because he wanted some way to test without people using their subjective opinion. You know, he wanted a procedure where you do a calculation, and if you get more than a number, you decide this, and if you get less than a number, you decide this. In other words, you take the personal decision-making out of the process. Yeah, do you understand? So that's why, you know, we seem like we're mechanical here. If it's less than 5, if it's more than 5, you know, we don't use our personal opinion here. Okay. 9, is it? Okay. A fortune teller claims she can predict whether or not a person is thinking of a cat or a dog when asked to think of one. A researcher tests this by having her predict what animal 10 people are thinking of, and it was found that she was right for 7 of the predictions. Is she psychic? Now, I'm going to change the answer to this question because I just copied something. Okay. Right. My answer at the back is wrong. But I wonder if anyone can spot what the problem is with this question.
The question says physics, but then the answer behind is calculus
Wait, say that again. Repeat from the beginning, a little slower.
The question mentions the fortune teller predicts, that means it's one tail, but then the answer behind is two tails.
Yes, that's definitely wrong, but there's something else more wrong than that. Anybody spot anything very wrong with the question? Now, I'll tell you what's wrong. I'll give you a hint, okay? Yeah? It is something to do with the predictions, but not the 7 necessarily, huh?
Then the answer is 0.5.
I don't think it's that.
Does the cat, the dog, whether if it's right or wrong?
I'll tell you, look, guys, there's something you're all assuming that I never actually said in the question. What are you assuming that I never said in the question?
That they're all different people.
Okay, let's not go nuts, Angela. We can reasonably assume that they're all different people, yes. Yes. But there was something unreasonable to assume. It's unreasonable to assume that people will tell the truth, yeah, but will equally pick cat or dog. Okay? It's not like flipping a coin. Suppose, for example, that it's known 70% of people would pick a dog over a cat, for example. Then that means, as a fortune teller, all I have to do is keep predicting dog, and in a group of 10 people, how often would I be right? I'd be right 7. So, it's actually, it's actually possible that people would pick dog 70% of the time, and if a fortune teller predicts right 70% of the time, that just could mean they've predicted dog every time. I'll give you another example where you see this in statistics. Suppose 10% of mornings it's raining. Okay, now I tell you I can predict whether it rains tomorrow or not. If I'm right 10% of the time, then all I'm doing is saying every morning it will rain, because 10% of the time I will be right. So it's important to actually know what the underlying rate is, and the underlying rate of picking a cat or a dog you don't know. So for this question, the answer is you can't know, because you don't know at what rate people would choose cat or dog. I'm sure there must be some kind of bias. Like, for example, if I'm in a Muslim country, would I be right in thinking, if I ask people to think of an animal, a pet, a cat or a dog, they'd probably be more likely to think of a cat? Would that be right? Yeah, because dogs are haram or something. Yeah, something like this. Give me a break here, okay? You get what I'm saying, right?
Yeah.
Whereas, I don't know, maybe in some other country, it'd be the opposite. So, like, for example, if this fortune teller, well, it's hard to imagine, if this fortune teller was in a Muslim country, perhaps she could just predict cat, and I would believe that she would be right at least 70% of the time. Yeah. So the answer here is we don't know the we don't know the rate people choose cat or dog. So we can't actually test anything here. Okay, can I scroll down? 10. A sample of 30 windscreens is tested for safety from a car company. In total, 2 of the windscreens failed the test. Test at 1% level that the failure rate is better than 10%. Okay. So the null hypothesis is that the failure rate is 10%. And the alternative is that it's better than 10%. And better in this context means less than 10%. So the p-value will be the probability. Now, how many did we get that failed? 2, was it? 2? So it's 2 or fewer. Yeah? Now, do you have a table that goes to 30? I don't think you do. No, but that's okay. Oh, you do? Okay, great. It goes up to 30? So this is table 30, 0.1, and 2. What do we get? 0.4? Okay. That's what I have at the back. It is, okay, that's pretty high. So, yeah, it's pretty big. So, the only difference in this question is I ask you to test at 1%. Oh, 114. 0.4114. Like this, okay. I ask you to test at 1%. So, this is definitely more than 1%. We do not reject. Yeah. It's kind of an irrelevant point because even if I said test at 5%, it's still the same conclusion. 11. A farmer is testing a new seed. He tests a sample of 20 seeds to see if the new seed is better than the old seed for germinating. Typically, 75% of his seeds germinates. So, if he had 20 seeds, he would expect 15 of them to germinate anyways. What would be the critical values for him to be convinced the new seed is better? What would be the critical values for him to be convinced the new seed is different? Okay, so what's different in this question is we want to calculate first what number would he need to get so that he thinks, oh, the seed's actually working. So the null hypothesis is that the probability is still 0.75. And the alternative hypothesis is that the probability is better than 0.75. So is this 1 or 2 tails? 1. Now, imagine that he got heads, or not, sorry, not heads, germinate 15 times. Would that provide evidence that the seed is doing anything better? What do you think? No, it wouldn't. Because remember, how many seeds does he normally expect to get to germinate? 15. So if he got 15, no good. So he would certainly want to see more than 15 germinate, right? So my question is, at what point will he get enough that he says, yep, I think this is working? So we have to work out this backwards. We need to figure out at what point here will we get a p-value of 5%. So we're literally working out backwards here. The p-value needs to be 5% or less if we have to round off. So we'll try to be as close to 5% as we can. Okay, so do you know what? Actually, rather than writing less than 5%, I'll write roughly equals 5%, but we'll probably have to round. So we'll always round in favour of making it more convincing. So we're saying probability of x or more is roughly 5%. That's 1 minus the probability of x or fewer is roughly 5%. Yeah? Now, this is, yeah? 1 minus table book, 20, 0.75 and x. That's roughly 5%. So you want table book 20, 0.75, x to be roughly 0.95. Now 0.95 or a little bit better if we have to round off. What page are we at now? Page for the 20. Here we go. Oh, but I forgot, we can't look up 0.75 because it only goes up to 0.5. So we'll have to make a little bit of a change here. So rather than looking at germinating, should look at non-germinating. Alright, so just be very careful here. In this one we're looking at x or fewer germinating, which means this is x or, stay calm, x or fewer germinating, so 20 minus x or more not germinating. Yeah. But of course we can't look up or more. So okay, so one step at a time. This is the same as table book 20, 0.25. This is the same as probability. This is x or fewer. This is 20 minus x or more not germinating. And you want that to equal 0.95. Okay. But you can't look up or more. So now this is 1 minus the probability 20 minus x or fewer not germinating, which is 0. So we're actually back to 0.05. So this is the table 20 minus x 0.25. Oh, what am I doing, Stephen? 20 0.25 20 minus x equals 0.05. So if we go to 0.05, 20, and we're no, not sorry, yeah, 0.05. No, 0.25, 20, and we're looking for 0.05. Now you see that when we have 1, we have 2%, and when we have 2, we have 9%. So we don't want to be too far past 5%. We would prefer to be under than over. So I should choose the value that gives this 1, which means x equals 19. So that means he would need to get 19 seeds to germinate so that he can be convinced that the new seed is germinating at a better rate. Yeah. I think it's because there's only 20 seeds to begin with. So it could actually naturally vary a bit. So this is x equals 19. Okay, that's very hard. That's very hard. Now I think, yeah, so B now. Oh yeah, of course. Probably want to, huh?
Yeah.
Right. How far back do I need to go? Is this more?
Oh, no, just a little bit. Yeah.
Like this? 19 or 20 is the answer here he would need. Oh, in the book I wrote 18. I think that's wrong. That should be 19 or 20. 19 or 20.
Maybe you want to do the 0.09.
Yeah, that's what I think. That I did one extra, maybe. Okay.
Well, I don't understand what you meant by would rather be under than over.
Oh yeah, because we want to reject the hypothesis. So we reject if it's it's under 5%. So
You always go below.
in these types of questions, yeah, always choose the value that will give you a p-value of no more than 5%. You want to be under 5% always. Like, I suppose think about it like this. If all 20 seeds germinated, that'd be convincing evidence. And what we want to do is we want to move down until we reach the critical point where we would get 5% in our calculations. So since we're looking for support, then we would just stop short of that. We'd never want to go over into the next bracket. Is that okay? I know this one's very hard. Unfortunately, I saw this in the exam once or twice, so it does come up. Now, I think they make it a smidge easier because here the probability was 0.75, so I had to mess about a little bit. I think in the exam they would make it like 0.4 or whatever, so you could look it up more easily in the table book. Okay, B. Can I go on to B? Not yet. Yeah? Can I go on to the B part?
Yes.
Now, the second situation is just, it's nearly the same, except the farmer is just wanting to know, is the seed different? You know, it's possible that the new seed actually is worse. So now we're testing the hypothesis that the germinating rate is 0.75. And the alternative is that it's not 0.75. So, like I said before, if he got 15 of them to germinate, that would be supporting his idea that, oh, it's still the same, okay? There's some point here, we'll call it X, where it's so high he thinks that it's different. And on the other side, there's some point here where it's so low that he thinks it's different. Now actually, to make it a little bit easier, I'll call this X. So let's say X here is whatever, 2. Then this number up here would be at 20 minus X. Because it'll be a mirror image. That's the nice thing about the two-tail calculations. I don't know if you've noticed it. It's symmetric. I think it's symmetric here.
But if we already calculated X.
For one tail. Yeah. Is it symmetric here? Do you know what? Even if it's... No, it has to be symmetric because if it's not symmetric, we don't have enough information. Like if it was two variables, X and Y, for example, then you would need this and this to be 5%, and we wouldn't know how to distribute them. Yeah, so we have to say they're symmetric. Okay, so that's nice. That means we just have to look up, we just have to do half this problem. Because this one here should be 2.5% and this one here should be 2.5%. Because remember we said this, both of them have to add to 5%. We did one like this. So we can actually reduce our work in half here by just looking at half. And which one will I choose? Which would be easier to look at? This one here, because it's already in the form of less than or equal to x. So we want the probability of x or fewer, and that's to equal 0.025. Yeah, so we'll have to flip it then. So it's x or fewer germinate. But the problem is with that is the germinating probability is 0.75. So we'll do 1 minus the probability. No, sorry. We'll do. Oh, so you're thinking it might be easier to look at the other way, and then we have to flip it then. Do you need me or them? Surveillance.
Yes.
Okay, I'll continue then. So I think you're right. It might be easier if we look at the flip side at the beginning, because then we'll have to flip it back then in a moment. So let's look at the other way around. This is the probability of 20 minus x or more germinating. That's equal to the probability of x or fewer not germinating. Mind blowing. 0.025. So this is table 20.25 x, and that's to equal 0.025. One. Definitely. Yeah? So that means x is 1. So that means if he gets 0, 1, 19, or 20.
That's what I asked them. This is the same thing that we got in 8.
Only by coincidence, because of the way the numbers worked out. Generally speaking, it wouldn't be the same, just by coincidence. Right? So I have my answer wrong at the back for this one as well. It should have been 0, 1, 19, 20.
But didn't we say 19 or 20 means the new seed is better? Or is it?
Yeah, so if he got 19, well, that's good. If he got 19, it would mean in the first test, he would have evidence that it's better. But then in the second test, he would have evidence that it's different. But you knew that anyways, because if I said to you something is better, it also means it's different. So the fact that there's an overlap here is a good thing, because you would expect passing the first test automatically means you pass the second test. So no, that's a good thing, not a bad thing. Okay. 12. I'm sorry to tell you, is exactly the same as 11b. If you look carefully, all I did was change the story, but the numbers are the same. Isn't it? No, something's not right with these. No, I'm doing something. Hang on, let me think. Something screwy's gone up with my tails. Something screwy has gone up with my tails. No, I'm sorry. I think I've screwed up. I think I've screwed up the calculations in question 11. Now that I think about it. Or have I? Ooh. No problem. What I'll do is I'll continue this with the next group, and I'll start from number 11 in the video. I'll recalculate it. I think I screwed up my calculation. I was thinking about it the wrong way. Do you remember earlier when I said germinating is 15? Yeah. And I was imagining that you come in a distance x from the left and the right. I think I screwed it up. I should have been doing it the other way around. I think. I'll need to check this. I should have been going x left and right from the centre, perhaps.
Yeah.
Now don't say yeah like you knew all this time.
No, okay. I
Okay, grand. No problem. If you just watch the video, I'll continue from number 11. It'll be at the start of the next video, okay? I'll upload this now.
I noticed what I was testing.
Sure. Huh? Have you not got class now? No, you can like and subscribe on YouTube.